agradecemos a nuestro señor director en este instante. Gracias.
Okay. Well, thank you very much indeed for all that wonderful introduction. And it's an enormous honor for me to be here as part of the series of the lectures in honor of Solomon Lefschetz, whose name I became acquainted with when I was first in Cambridge as a young graduate student, and many of his ideas were important at the time. I remember particularly the topology he introduced in algebraic geometry. I started off as a student in pure mathematics in algebraic geometry, and I developed my interest in physics slowly afterwards. One of my most intimidating experiences when I was a young graduate student, I had a supervisor who was William Hodge, and I was one of a small number of people working under him. And one of the other students there, I was asked I wasn't sure about the topic I was studying, and Hodge suggested that I might sit in the supervision of another of the students, and I thought, well, he's another graduate student. And I remember it was so high-powered, and I didn't understand a single word. And it was much later, well, not much later, that I discovered that not all the graduate students were like Michael Atiyah, and he was the second of the Lefschetz lecturers, and a very, very distinguished mathematician. So I thought they were all like that, and this was, terrifying. Anyway, I haven't come to talk about that here. I was going to talk about my crazy ideas about cosmology, and I apologize for using this old-fashioned, well, it's a combination of old-fashioned and modern techniques. And this is a title I have. A title I've used for a lecture like this on other occasions. So it's Before the Big Bang and Beyond Eternity. And that's more or less what I shall talk about. I'm using two of these gadgets, so I hope that I won't get lost when I'm walking backwards and forwards. Okay. I wanted to, first of all, give you a picture of the universe. So here is the universe. According to the current picture we have, I should prevent myself walking too much. This is a space-time picture, and many of my diagrams will be space-time pictures. So here we have time going upwards and space this way. So you have to imagine, as the universe evolves, space, which is you have to say it's three-dimensional, of course. I can't draw all the dimensions, but as time evolves, this will move up, and the section that this makes of this picture will be the universe at any particular time. Now you may worry about why it has all this frilly stuff at the back. This is because we don't really know whether the universe closes up or whether it is open. And there are the three standard pictures one has, very nicely illustrated by Escher, who for some reason, this is the Dutch artist, M.C. Escher, who illustrates many beautiful mathematical ideas in terms of very beautiful pictures. And the three possibilities on the whole, on the large scale, are that it's closed up like a sphere. Of course, it's a three-dimensional sphere, not a surface of 2 dimensions here, 3 dimensions, 3-dimensional sphere, or a 3-dimensional Euclidean space, or a 3-dimensional hyperbolic space. I'm going to say something more about this picture later, so let me not say much about it here. But you see the angels and the devils in these pictures. They don't quite know where they are. You see the angels and devils right up here. Think the space is just like the ones in the middle. I'll say more about this later on, because it is a good example of the kind of geometry which is known as conformal geometry, which will play a big role in what I have to say. Now let me go back to the picture of the universe as a whole. Here we have the Big Bang, which is meant to be the beginning, time going up. And one thing that the experts will worry that I may not have depicted in this picture, I should perhaps point out where we are. We're about somewhere about there. Maybe that's us there. And one thing that people might worry about is in the very, very early stages of the universe, something called inflation was supposed to have taken place. Now, I have not shown inflation in this picture for two reasons. One is, well, maybe I have shown it in the picture because it would be so small in the picture that you wouldn't see it. It would be hidden in that little spot at the beginning. So we need a magnifying glass to have a picture of what it looks like. And here is what we would see. This, of course, is the handle of the magnifying glass. And here we have the Big Bang, but initially an exponential expansion. Exponential means that at any one time it is similar to what it was like before. So the expansion rate is proportional to the size of the model. And the point I want to show here is that this postulated initial state called inflation is very, very similar to what we see now, but on a completely different scale. So that's the picture people have, is that there is an exponential expansion which we believe to be holding in the very remote future. You see already, because we're about here, you can already see the beginning of this expansion. And this observation won the Nobel Prize a few years ago. Very impressive observation, which tells us that the universe is expanding, beginning to expand in this exponential way. It's what people call dark energy. I'll say a little bit about that later. I don't like the terminology, but that's what people call it now. It's really can be understood as Einstein's cosmological constant, which he introduced he introduced general relativity 100 years ago in 1915, and I think it was 1917 when he introduced this term, which gives you this exponential expansion and what we now call dark energy. But he then retracted. He thought it was a mistake, and we shall see here that even Einstein's mistakes seem to turn out true. This is an example of it. Now, I want to say something about this model. I want to do two tricks to it. And these tricks are very useful in understanding the geometry. One of the tricks is to expand out the Big Bang, and the other trick is to squash down infinity. I should say that the trick about squashing down infinity is basically the same trick as Escher is making use of here, where the infinity of this universe is a boundary to the universe. So it has this character that you can squash down the model so that what should be infinity is really a boundary. And it's a very clever representation. It's called the Poincaré representation. I suppose, like so many mathematicians, it was actually due to another person, who's Beltrami. Poincaré did rediscover it, but Beltrami was the person who thought about it first. And it's a similar trick, where infinity gets squashed down by one of these transformations, which is conformal. And I should say, conformal means that little shapes are either stretched or smaller, but uniform. So they're stretched as much this way as that way. They're not distorted. And if you could see the shape of the eyes of the devils, for example, you would see those shapes would be completely similar right the way down to the edge. Now this is the kind of thing we're doing here. We're squashing infinity down, and in squashing infinity down, we can, as I say, let's say these two tricks out here. One of them is to squash infinity down. Is that the one I'm doing? Not worried that I have the wrong picture here. I don't think it makes too much difference. Anyway, we squash infinity down, or we stretch out the Big Bang. And those two things are what we want to do here. Squash infinity down, stretch infinity, stretch the Big Bang, and it's a little bit easier if I can use 1 minute. I thought I had another. picture which would be more useful here. It doesn't matter. Ah, no. I think I left it at home. Never mind, it does not matter. Let's squash it down, but we can't do it too well here because that picture is too big. So let's take a slightly smaller universe. There we are. It's the same universe, but drawn smaller. And here are the two tricks. One of them is to expand out the Big Bang, and the other is squash infinity. And it's nice because you can draw the whole thing in a little picture. Now, I want to say something about these two tricks. One of them is that it works under very general circumstances. So the squashing of infinity, due to a theorem due to Helmut Friedrich, under very general circumstances, as long as this thing called the cosmological constant, which I call lambda here, as I said, that was dark energy that Einstein introduced in 1917 under a different name, and this enables you to squash infinity down by this conformal squashing. And as I say, it works under very general circumstances. Now the other trick of expanding out the Big Bang is an extremely strong restriction. In the normal cosmology models, which are symmetrical in every way, they have the fact that you can do the stretch. But if you take a very general model which has irregularities in it, you can do the one in the future, that's what this theorem says, but you cannot necessarily do the one in the past. Okay, that's nothing particularly controversial that I'm saying here. This is straightforward, except that, as I say, it's a strong restriction on the Big Bang. And you might ask why we should be interested in making such a strong restriction. Now, I want to, as I said, this is not crazy yet. I want to show you what, however, is crazy. And crazy is not bad. So you have to distinguish between these things. You have to be a bit crazy, especially in cosmology. Because well, the Big Bang is crazy already. And also, is this expansion here, this is crazy too. So it's not so bad to have crazy ideas, as long as they're the right crazy ideas. But this is where I introduce my crazy idea. Okay, what started the Big Bang? The usual idea is, well, the Big Bang was a singularity. Singularity means that your equations go to infinity, things will go wrong, and your equations don't work. And so therefore you say, well, at the Big Bang, the very notion of time has become meaningless. And therefore you can't ask what went before the Big Bang. I remember Stephen Hawking making that statement. I would have agreed with him too. However, I'm now changing my mind, and I say it does make sense to talk about what was before the Big Bang. And what was before the Big Bang, in this crazy idea, was something very similar to what we have now. So I'm calling from the Big Bang to the exponential infinity expansion, one eon. So I call this an eon. And this is, there was an eon before our eon, another eon before that. There will be another one after our eon, and then another one after that. And presumably these would continue indefinitely. And the idea is that the stretched Big Bang is a continuation of the squashed infinity of the previous eon. So that's the crazy picture, and you have to get used to it, because, well, I'm going to try and explain why it's perhaps not so crazy. So I have to try and give the reasons behind this suggestion. And in fact, there is a very important principle in physics, one of the most fundamental physical principles, which, as far as I'm aware, this scheme of mine is the only one that I know of which accommodates this principle in physics. And the principle is a very well-known one, known as the second law of thermodynamics. Now, what does the second law of thermodynamics say? In some sense, it's very obvious. It tells you that things get more and more random. So if you have some system, you just leave it, it gets more random. So if you have a cup of coffee, you put some sugar in it. People don't do that much now, but remember sugar in coffee. And then, if you leave it long enough, it dissolves and it gets mixed up. It goes in that direction. So the sugar and the coffee become sweet coffee. Okay, now, but it doesn't go the other way. So it gets more random, that the sweet coffee is more random than the sugar and the coffee together. And many examples like that. You see, you could have a coffee cup on the edge of the table, and you knock it off onto the ground, and the coffee spills out like that. That happens if you're clumsy. If you're clumsy, you can't do the opposite thing. You can't do the opposite thing even if you're clever. Why can't you do it? Well, you say, suppose we're just thinking of Newtonian dynamics. The laws are completely reversible in time, and that's still true basically basic physics. The laws are the same if you go backwards as if you go forwards. So why don't you see the cup jumping up onto the table? You only see it going that way. Well, you say there's another principle, the principle of the second law of thermodynamics, which tells you that the randomness, I'm going to use the technical word entropy, the entropy is increasing all the time. So the word entropy, for our purposes here, means randomness. Okay, I could be more technical about that, but I'm not going to be that here. So the entropy increases with time. So what does that tell us? That tells us that the Big Bang must have been a state of very low entropy. Okay, so why do we believe that there was a Big Bang at all? Well, there are all sorts of reasons. The galaxy is expanding away from us. But one of the most important reasons that it gave us a good impression of what the Big Bang was like, and it was there at all, is the observations of this radiation, which is coming in from all directions, known as the cosmic microwave background, CMB, we tend to call it. That won the Nobel Prize twice, which is interesting, on two completely different occasions. One was the initial observation by Penzias and Wilson, sort of by mistake. They discovered this radiation coming in all directions, and then the various observations about it, detailed observations, were made later, one of which is the following. Now I want to say something about this. This is the spectrum of the cosmic microwave background. So if you look at this radiation, which is electromagnetic radiation, light of a much longer frequency than ordinary light, and we plot this way, the frequency, it's composed of many different frequencies. These are the frequencies this way, and this is the intensity this way. And what you see, this is an old slide, but I asked one of the people who produced it, is there a modern version? He says, no, we use the same one. So this is the one which basically came from the second Nobel Prize that was won for the cosmic microwave background. And we see this curve here. I should explain that the solid curve, this line here, is the famous Planck curve. This was introduced by Max Planck at the beginning of the century. When I say the century, you see, when I say the century, of course, I'm talking about the century that I still live in. People tell me I'm still in part of living in the last century, and I still live in the 20th. Well, that's the 20th century, just to get them straight. Okay. Anyway, at the beginning of the 20th century, Max Planck, with a very simple but crazy idea, I'm saying crazy ideas are not so bad, crazy idea is that energy could come in these little parcels in proportion to the frequency. We'll come to that again later. But using that idea, he was able to work out this curve, which is what's called the black body curve. I'll say a little bit more about that. But what this seems to fit, these little lines going here, are to say that the the observations, there are certain errors. So these are error bars here. But these bars are exaggerated by a factor of 500. So you have to divide even the longest one here will look like a little point on the curve. So I'm trying to say that the theoretical curve, Max Planck curve, agrees with the observations to an extraordinary degree. Now what does this tell us? This is the key point I want to say. What was Max Planck doing here? He was talking about the radiation spectrum in what's called the black body spectrum. What does that mean? That means thermal equilibrium. What does thermal equilibrium mean? It means maximum entropy. Maximum entropy. So what we're seeing when we look at the very early universe, well, the CMB is one of the very earliest things in the universe. Well, it was a few 100,000 years, maybe after the Big Bang, but that's pretty well the Big Bang. And this is telling us what the Big Bang was like. What was the Big Bang like? Thermal equilibrium. Thermal equilibrium, what's that mean? Entropy maximum. That should be a little bit of a puzzle to people. And I've always wondered why cosmologists didn't say, what? Isn't this crazy? It's not just that. This was what they expected. It's a complete expectation. But it's crazy. Why is it crazy? Well, I just said, the second law of thermodynamics tells us the entropy is going up and up and up and up. But if it started at the highest point, how can it be going up and up and up and up? Okay, well, I think people thought, oh, well, the universe was expanding, and so for some reason maybe there was more room for more entropy. That's wrong. That's completely wrong, because the dynamics is reversible, and that's not the answer. I want to give you what is the answer. What the answer is that what we're looking at here is radiation which was in thermal equilibrium with matter, so maximum entropy state, all jumbled up together with whatever matter there was around them. And that was indeed in thermal equilibrium, apart from the expansion. And the expansion is not a factor. You state this right. There was a distinguished cosmologist who was around when Einstein was around, called Coleman, and he understood this completely well. There's no problem about the expansion, that's taken care of. The problem is something completely different. And the answer to this problem is, what we're seeing here is light coming from matter. What we are not seeing in this is something else. The something else is also in the CMB, but it's to do with the uniformity. We see, as we look all different directions, the temperature, a very cold temperature, just a few degrees above absolute zero, that very cold temperature, I mean it's cold, but it used to be very hot, you see. It's cold because the universe expanded. But this temperature is very uniform over the sky. Well, it's not quite uniform. In fact, it's not quite uniform. The main reason it's not uniform is because the Earth is moving through it. And the motion means that as we move into it, it looks warmer. And when we move away from it, it looks cooler. I don't know which way I should be pointing, but whichever we're moving, it's warmer in that direction and cooler in the other direction. Just a little bit. You correct for that. Correct for that, and you see a temperature which is uniform to about 1 part in 100,000. Something like that, very uniform. Now that uniformity would also be consistent, you might think, with a high entropy state. And let me give you a picture here. The sort of thing that people talk about in discussions of the second law of thermodynamics. The entropy is this measure of disorder. They would talk about a gas in a box. So let's think of a gas in a box, and let's suppose that initially you had a little compartment and the gas was all in that compartment. You remove the walls, the gas will spread out over the box. This is time increasing and entropy increasing, second law of thermodynamics. And here it is, very uniform. So you might say, oh well, yeah, uniform agrees with high entropy. That doesn't help. We want low entropy. How can it be low entropy? Okay, here's the key point. Introduce gravity. Consider gravitating bodies. So this picture now is like that picture, but now think of these as stars. The box is a ridiculous, enormous box with a lot of stars, a galactic scale box, and there are a lot of stars running around it. And because of gravity, it will start to clump, and clump more and more, and then the maximum entropy is still entropy increasing, but you get less and less uniformity. So everything else, pretty well, apart from gravity, will follow this route. Gravity follows that route. What we see is uniformity. But does that tell us that it's high entropy? No, because in gravity, it's low entropy. What we're seeing is a combination of this and this. And the low entropy is all in gravity, which is a very remarkable fact. In a way, it's almost even more uniformly over all physics It's low entropy only in gravity. And that's what we seem to see. And this is very important for us. You might say, why are we all here? Why are we alive? All these things depend on us taking advantage of an important source of low entropy. What's that source? That source is the sun. And the sun is a bright spot in a dark sky. And well, you see, sometimes people say, well, we get energy from the sun. Isn't that wonderful? But we don't. We don't get energy from the sun. But when I say we, I mean the whole planet. Because the planet gets energy from the sun in the daytime, and then at night it all goes back again. Pretty well. There's global warming too, and I don't want to dismiss that because that's important. But on this scale, it's not a big factor. Now, the big factor is the following, is that the sun is a hot spot in a dark sky. Hot means that the photons are, well, you see it's yellow, and the light going away is infrared. The photons here are individually more energetic by the Planck formula. That's Max Planck again. The ones going away have a lower frequency, and therefore individually they have a lower energy. Therefore we need more of them. Not so many photons come from the sun, lots and lots go back into the sky. So the energy here is distributed over a smaller number of degrees of freedom, and that means low entropy. This point was emphasized by Schrödinger in his book, What is Life? It was very insightful. A lot of people complained to him that he was right. And you see here, the point is we don't get energy from the sun, we get energy in this form, which is low entropy as compared with what goes away. Now, of course, the sun, there are all sorts of complicated processes going on in the sun, nuclear processes and so on. But the key point is the sun is there. The sun would be there and it would be hot quite independently of all the nuclear forces. In fact, if it were not for nuclear forces, the sun would collapse faster, get hotter, and then die. The nuclear forces keep it going without it getting too hot. And it's useful to us, but nevertheless, the key point where it all comes from initially is the gravity which produces the sun. So the sun is there at all because of gravitational pumping. So it is the same effect. Well, you see, I'm saying, well, this energy is conserved, but the entropy, you keep it down, plants make use of this temperature variable, or the high energy of individual photons. It's all very complicated, but the fact that life is going is because of this imbalance. If the temperature of the sky were the sun all over, it would be completely useless. It's the low entropy is in the temperature difference here. Sun is a hot spot in a dark sky, and this comes about from gravitational clumping. So it's the key issue. That is the place where entropy was low, is why we exist here at all as living beings, because these things, as they clump, get hot as well. Okay, that's a sort of a complicated story in a nutshell, but I think it's an important story. And I want now to say more about this very high entropy state, the black holes, because the black holes will be important in what I have to say here. So I want to give you a picture of a black hole. Well, some of you might have seen what this television thing was like. To me, that didn't look anything like a black hole. What does a black hole look like? It looks like this. Because, as I said, my pictures are space-time pictures. This is the matter in the black hole, in the star, or whatever it was, say a star, was collapsing. It got too big. The forces couldn't hold it apart after a while, and it started to collapse inwards. And as it collapsed inwards, it distorted these cones. I have to tell you about the cones. This is a key thing in what I want to say. So these are the light cones, or the null cones, and what are they? Well, I don't lose that one. A light cone. Technically, I should call it a null cone, but never mind, we'll come to that. You have to think of any point in the four-dimensional space-time, three-dimensional space, one time, at any point in that space, there will be a little cone sitting there. Geometrically, it sits there. And what that describes is what light would do. It doesn't have to be any light there, but if it were, it would follow the cones. So this tells you the speed of light, if you like. So if you imagine there was a flash of light at that point in space-time, as the time evolves, that flash gets bigger and bigger and bigger, and here's a spatial picture. There's the flash. This, I have to drop a dimension in representing the picture, never mind. That thing that looks like a little circle is really that sphere surrounding that point. This thing, which looks like a somewhat bigger circle, is that bigger sphere. So as time progresses, it's the flash, there. But space-time terms, it's this cone. We like to have the past cone too, which is what the converging flash coming into that point would be like. So space-time has these things sort of painted on it. That's what you have to think of. The most important part of the geometry of space-time is that each point has one of these little cones. Now, Einstein's special relativity is where these cones are all uniformly arranged throughout the whole space-time. There's a future cone and a past cone. Light ray, a photon, is a line. The history of that photon is a world line which is everywhere tangent to the cones. A massive particle is not allowed to go faster than the local speed of light, so it has to have a world line, that's its history, which lies within the cones. So a massive particle is always within the cones. In general relativity, these will not be uniform, they'll be one way or another, and you will see from the picture over here that the light cones get very distorted in the case of a black hole. And there's this thing called the horizon, where these cones are tangential to this vertical line, which is the sort of what you think of as stationary in the picture. But then they get tilted more and more to go inwards, and it's bad news if you happen to fall into it. You were directed into this nasty thing in the middle, which is the singularity where the space goes crazy. The space-time goes crazy, the curvature of space-time goes crazy, and everything gets destroyed. I've got a symmetrical picture here. This is due to the original Schwarzschild solution and the picture of a collapse, which was due to Oppenheimer and Schneider. But if it's irregular as well, it doesn't change very much from this picture. The singularity will look very much more complicated, but it's more or less the same picture. If you are looking at the black hole from the outside, your light ray, the photons that get you into your eye, you follow them back. Because the cones are tipping over, you will see this body just before it crosses the horizon. It'll fade away very quickly because the thing gets very redshifted. But that is the picture of a collapse through a black hole. Okay, so we have our black holes now in space-time terms, and I should put them into my picture. You see, I can see it. Here's the universe. Before. And I now want to put some black holes in it. I'm going to put the singularities in, don't worry about the horizons. So we have a lot of black holes. Here we go. Now you can see what's really going on in the second law on a very big scale. The Big Bang had a singularity which was very low entropy. The black holes have a very much more complicated structure, singularity, which is very high entropy. And the sort of progression of entropy, well, if you imagine a theoretical being created in the Big Bang and who falls into a black hole, then the past of this being would be very low entropy singularity here, Big Bang, and a very high entropy singularity here. So the second law is represented, crucially, in this difference between the singularity structure. So that's what we have. Now, I want to show why, you see, why did people introduce inflation in the first place? There are all sorts of reasons. The original reasons I always thought were pretty bad reasons. There are some good reasons, but it is still part of modern cosmology. So there are some definitely good reasons. But the bad reason that people used to emphasize was the universe is very uniform, and this uniformity came about because of this exponential expansion which took place, the theory says, in this inflationary phase, which was something like 10 to the minus 36 seconds, ridiculously tiny time after the Big Bang. Now, the idea is that expansion smoothed everything out. Now, I want to say why I never believed that. And the reason is very simple and straightforward. And let's imagine that we have a universe like this, but it's collapsing. Okay? Einstein's equations are symmetrical. If that's a solution, that's a solution. Okay, time is going this way. But suppose it's not the exact symmetrical cosmological model, but we have a little irregularities. And those little irregularities are going to develop consistently with the second law of thermodynamics. And remember that the entropy goes up when the matter collapses, and this produces black holes. Now these black holes will eventually start to congeal with each other and form one unholy mess at the end. So this is the type of singularity that you will generally get in solutions of the Einstein equations. It's worse than the black hole singularity because it's a whole congealing of black holes all over the place, forming an incredible mess. So this is an absolutely huge entropy. That is an extraordinarily probable type of singularity. If you chose your singularity randomly, it would look like this. Okay, what about the Big Bang? This is a very special singularity. If you chose it randomly, it would look like that. Well, it wouldn't look like that. It would look like whatever. It would be a mess. And inflation doesn't help. You could put inflation into your equations here. There's a thing called the intertone field. That's what people do. You put it in the equations here. If that's a solution, that's a solution. It doesn't help. It depends on the initial state before inflation being very, very, very special. It just pushes the problem somewhere else. It can't do anything else. There's no question about it. So, I mean, it's not that I'm not using any equations here. It's just a general feature of the whole situation. So, much more probable is that this is extraordinarily improbable. In fact, you can estimate how improbable it is. That estimate comes about because of the Bekenstein-Hawking formula, which tells you the entropy in a black hole. And that entropy tells you how unlikely, or how much more likely the black hole is than not having a black hole. So, how much more likely is that than that? Well, you can estimate it. Here's the estimate. It's about 1 part in 10 to the power 10 to the power 124. Now, of course, mathematicians know what this means. But if you're not a mathematician, you might not be double exponents, may not be familiar. It means you 10 to the 124 means that you've got 1 with 124 zeros. But now this is 10 to that. So this means that this number has so many zeros that if you try to look at all the different protons in the universe and try to put a zero on each one, it would not be nearly big enough. So this is huge. And this is telling you how unlikely the Big Bang was. It was not a random event by any chance, with inflation or without inflation. It makes no difference. Well, okay, you might fiddle with this number. In fact, I used to say 123 up there. But since dark matter, don't confuse with dark energy, dark matter has become well established, it just pushes this number from about 123 to 124. It doesn't make the slightest difference to the argument. It makes a huge difference to the number. It makes an absolutely stupendous difference to the number. But to the argument, it makes almost no difference. Okay, so this is what we have to contend with, this absolutely huge number. Well, before saying what is the explanation of this extraordinary precision, what was the nature of that precision? And the nature of that precision was in the nature of the singularity. Now, I used to phrase this in a way, I said, well, there's a thing I call the Weyl curvature hypothesis, which said that a thing called the Weyl curvature was zero in the Big Bang. It's a hypothesis. One trouble with saying that here is I have to explain what the Weyl curvature is, and mathematicians would know what that is, but I take it that most of you don't. So let's forget about that. My colleague Paul Tell had a much nicer way of saying it. Well, I'm going to keep it a secret from you at the moment by not supplying that other part for transparency. I'll come back to that. But in order to talk about it, I want to talk first about the remote future. Now, what will the future be like? The universe expands and expands and expands and expands, and it gets colder and colder and colder, and it eventually gets so cold that some of the very coldest things in the universe start to get the hottest things in the universe. What am I talking about? I'm talking about black holes. I mentioned the Bekenstein-Hawking entropy. I want to mention the Hawking temperature. A black hole is not quite an absolute zero as temperature. It has a temperature. And that temperature depends upon the size of the black hole. The bigger the black hole, the lower the temperature. So the hottest black holes around will be the smallest ones. What are the smallest ones we expect to find? Well, these will be collapses of stars which are maybe about 10 times the mass of the sun. That sort of general order. How hot are they? Well, think about roughly like the coldest temperature that has ever been artificially produced on the Earth, and you're in about the right scale. Cold, in other words. So the universe will expand, a lot more expansion, but it's doing the exponential expansion, so it won't be hugely long in some sort of terms before these black holes will be the hottest things around. They will start to evaporate away, and the bigger ones will take longer. We know we have very big black holes. Our galaxy has a black hole in its center of about 10 million times the mass of the sun. So it's about 10 million times, sorry, 4 million, I said the wrong one. It's about 4 million times the mass. There are bigger ones in other galaxies, much bigger ones. But let's think of that, that's pretty big already. So that's the black hole in our galaxy. And that will take a long time before the Hawking radiation, the universe has to cool down and then it becomes hot, and then radiation from that black hole, this is a space-time picture again, comes away and takes energy from the black hole until eventually it disappears with a pop. I'm calling it a pop rather than a bang because, okay, it's a nasty explosion. I wouldn't want to hear it. But it's cosmological scales, it's nothing. Okay. I mean, all the energy from the mass of that black hole is coming out over this huge history of it. And a little bit left, but yeah, it comes out pop. We don't really know what happens here, but it's a minor thing. Maybe theoretically a major thing, but a minor thing with regard to how much energy is produced. How long will this take? Well, think about the biggest black holes we know are out there, that are observed now, and something like some 10 to the 10, 5 times 10 to the 10 solar masses, something like that. Okay, they're huge. How long will they take? Well, the length of time is drawn in this picture, not to scale, I'm telling you, is something like 10 to the 100 years. So you're thinking of, well, 10 to the 100 is sometimes called a googol, something like a googol years. So you have to wait that long before all the black holes are gone. Now that gets you to what I refer to, let me get my universe picture if I haven't lost it. I've lost it. Here it is. That gets us to the black holes are all going pop. This is not to scale by any means. The earlier ones were reasonably to scale. This is not to scale because 10 to the 100 years you have to wait. You get to what I call the very boring era. Before they go pop, that's the boring era. Because there's nothing around waiting except for black holes. Now, I think it's very boring to wait for a black hole to go pop. Very, very boring. But not the very boring era. The very boring era is when there are no black holes either. Now, I was thinking about this, people say you shouldn't use emotional arguments in physics. I'm not sure about that. Anyway, this is an emotional argument, I warn you. I was thinking, now that's a dreadful fate for our universe. Just to be very boring forever. And it's pretty exciting now, all sorts of things are exciting. And just to end up with this eternity is so incredibly boring. And so I didn't like that idea at all. That's what the current cosmology tells us. And I'm accepting that. I'm accepting the black holes will disappear. there's nothing left here, basically, but radiation. Mostly just photons. Now, photons have an interesting property. They have an interesting property that it is very hard to bore a photon. Now, there are two reasons why it's hard to bore a photon. One is they probably don't have any experiences whatsoever. Okay, that's not the reason I'm talking about here. The reason is something quite different. The reason has to do with relativity, and that is to do with clocks. Okay, we have now extremely, extremely precise clocks in nature. In fact, we have GPS, depends on the precision of clocks, how you drive your car, and the machine tells you where you are. Because the satellites and the signals that they send from them are so precisely measured, you take into account general relativity, all sorts of effects, and these depend on very, very precise clocks. Now, there are two kinds of very precise clocks, and the ones that are relevant here are in the case, come about from Max Planck again. Max Planck tells us that here's a particle, you see. Now, any particle is a sort of clock on itself. If it's a massive particle of mass m, Max Planck tells you, well, that its energy is proportional to its frequency. E equals h nu, h is Planck's constant, so that it has an energy which is proportional to its frequency. Einstein, these are the two most famous formulae of 20th century physics. Einstein, of course, is the most famous one, E equals mc squared. Einstein tells us that energy and mass are equivalent. Planck tells us that energy and frequency are equivalent. Put them together, mass and frequency are equivalent. So if you have a stable particle of rest mass m, its rest mass is its mass in its frame of reference, that mass is definitely proportional to its frequency. So it is a very, very perfect clock. And so the perfectness of the clocks that we have, atomic and nuclear clocks, depend upon these two formulae. It's very, very basic. Now, that means, you see, now I'm going to come back to the conformal geometry or the light code geometry that I had before. In fact, let me go back to my picture if I haven't lost it. I haven't. It's difficult to see these things here. Here we go. Remember that we had light cones everywhere in space-time. Now, the light cones don't give us quite the whole structure of the space-time geometry. You have to have the light cones, but in addition, you have what clocks measure. So you've got, here are two clocks. The history of the clocks, they're both perfect clocks and identical with each other, maybe clocks like this, and they're ticking away, and this surface represents what, the first tick, the second tick, the third tick. So in order to introduce clocks, I should say distances and clocks are equivalent. How do you measure distances? What's the most, well, we can talk about meters, and how do you know if something is a meter long? Well, you're supposed to go to Paris and take the meter, official meter, and see if your meter is as long as that. Well, that's no good now. It's not nearly precise enough. If you want a very precise measure of a meter, you just see how long the time takes to get from one end to the other, and use your very precise clocks, and that tells you what a meter is. But forget about meters. The clocks are the important thing. They tell you what the scale is. Now, the light cones that we have on our other picture there don't tell us the whole geometry. At each point, you have 9 independent components. They are the conformal geometry, as I said before. The scale is not defined, but the angles and shapes are defined by this. The one extra number you need to get the full 10 components of what is called the metric of space-time is these little surfaces here. Cones, 9 of them. The extra number is the surfaces. Mass is needed to give you the scaling. If you didn't have mass, you would have this geometry. If you just have photons running around, they know this geometry. Photons are solutions of the Maxwell equations. Maxwell equations, that's the equations of electricity and magnetism. They are independent of scale. They're what are called conformally invariant. So all they're interested in is these light cones. They don't care about the extra structure. And that's other massless things. It's true too. So I want to distinguish between these two pictures here. This is what does it demand? You see, it demands that in the very, very remote future, you only have things without mass. And photons will be by far the predominant matter in the universe. Forget about the rest of it for the moment. If it was just photons, they wouldn't even know whether this thing was squashed or stretched. So as far as photons are concerned, this picture makes perfect sense. This very stretched infinite geometry is just like a Big Bang. And the photons could sail through from one eon to the next without noticing a thing. You need mass to notice anything. Now there are particles with mass which will still be running around in the very remote future, even though they're very, very minority particles. And I have to introduce a hypothesis here. This is not conventional physics, but it's not inconsistent with physics that we know. And that is in the remote future, there will be a factor that mass decays away. We know that according to the Higgs procedures, we're told, in the very early universe, things are effectively massless, and they're massless because there's so much energy running around that the Higgs mechanism, as it's called, which gives mass to particles, is not activated. It's only activated a little bit after the Big Bang. Before that, there was effectively no mass. I'm saying there's a kind of converse to that, which is in the very, very remote future, again, mass fades out, and you have nothing but things without mass. That's a hypothesis. I'm not saying I have a good theoretical reason for that, but an indirect one which comes from this model. So that the picture that we have is... Now, wait a minute. I'm slightly confused by my pictures. I think I... Here we are. Sorry. Remember the Escher picture, which squashed down infinity to a finite boundary. So here we have something of that nature, but for the space-time as a whole, not just for spatial geometry. And this is like the boundary to the Escher picture, which, if I can locate that, is still a little uncertain. It's a bit dark. Never mind, I think you can remember it. Here we are. In the Escher picture, remember you could squash infinity down and it gives you a small boundary. Now this is a trick that you can apply here when you have a cosmological constant that is positive. So I need the thing that's called dark energy. Otherwise this wouldn't work. If it's there, and it is there, apparently due to observation, then we have a nice boundary which looks like it's just a surface that things could cross. I mean, photons could go across it, you see, because they don't care about the scaling. Infinite compression, the photons don't even notice it. So in the extremely remote future, well, you can read all this, but the main point I want to say is that with effectively massless particles, you don't have any clocks. In the conformal geometry, the light cones themselves are a sensible kind of geometry. Then you might ask, if it's a sensible geometry, what's on the other side here? Well, you might think it's a collapsing universe, but that doesn't work for various reasons. But the more sensible idea, I'm trying to argue, is that this was in fact, that was the other picture which I had before, which was I think I'm confusing myself by using two sets of slides which were different options. This was you see, according to this is quite standard in a way. So you get as I said, the Higgs mechanism hasn't operated until a little while after the Big Bang. So the particles are effectively massless. But my colleague Paul Todd had the suggestion that the characterization of this very special nature of the Big Bang is that it can be extended to something prior to it. So this is the picture that I have, is that prior to the Big Bang was a universe. No, it's all upside down. So this was the Big Bang now, and according to Todd, you characterize mathematically the special nature of this Big Bang by saying that theoretically you could extend it before. Now this theoretical extension, I'm saying, is not just a theoretical extension, but it's actually true of our universe. And what was before was the remote future of the eon prior to ours. So you see the kind of motivation in the picture I've given you before, and I think maybe that's enough to say about all this, is that it gives you a very nice picture where massless things can get across from one side to the other. The geometry here has to be of that very special kind. That number 10 to the 154 I had is automatically solved by saying that you have this continuation. So it's a mathematical trick, but I'm saying that mathematical trick is why we have this very special Big Bang. Now, there are two key points now I want to say about this. One of them is the story which started me off, and which you might quite reasonably worry about. See, I said, okay, this is to accommodate the second law of thermodynamics in the form that we have it. Second law of thermodynamics tells you entropy is going up and up and up and up and up. How can I have a cyclic model where the entropy is going up and up and up and up? Doesn't make any sense. I maintain that the answer to this is in the black holes. You see, I didn't say this, I think, but black holes have by far the most entropy in the current universe. If you take even galaxies like our own, but certainly the ones with much bigger black holes, the entropy in those black holes, according to the Bekenstein-Hawking formula, completely dominates the entropy in the universe otherwise. So those black holes are the culprits. Now what happens to those black holes? They eventually evaporate away. Now it's one of the great arguments in current physics, and that people worry. They say, well, Hawking originally said that black holes, well, there's a thing called what people refer to now as the black hole information paradox. So Hawking said that the information was lost in black holes. Now, he then, later on, retracted and changed his mind. Now, it has the advantage here that whichever side of this argument you're on, you have Hawking on your side. Now, I'm claiming it was I always have trouble saying the old Hawking. I don't mean the old Hawking, I mean the young Hawking, but the Hawking of a long time ago. So the old Hawking in that sense was right, and the Hawking of now, I'm claiming is mistaken. That's what I'm trying to say. I mean, he was right one of the times anyway, whichever. So that's all right. Now, the point is that these black holes do swallow information. Now, one reason why physicists don't like that is that they say, well, there's this principle in quantum mechanics that's how it's called unitarity, and one of the implications of unitarity is that information can't get lost. So, well, how can you have that? Well, I claim that I just think quantum mechanics doesn't hold at those levels. And this is one of the arguments why. That when you have big enough things which involve gravity, this principle of unitarity is not true. And there are other reasons which I won't go into here, but they have to do with measurements and so on. So unitarity, I say, is an approximation that on the scale of black holes, it simply isn't true. And the information is lost, and that is the answer. That the black holes most of the entropy goes into the black holes, they evaporate away, and the degrees of freedom that contributed to the entropy when those black holes are gone is gone. And that brings the entropy down. See, it's not that the second law is ever violated. It's not violated. It's what I call transcended. Because the second law depends on what degrees of freedom you think there are in the universe. And if some of them are gone, then you have to think again. You say, well, which definition do I take them into account or don't? You say, well, it's unreasonable now to take them into account. And if I don't take them into account, the effective entropy is down. If I did take them into account, the entropy would be going up and up and up. There's not a contradiction with the second law. But you have to bear in mind that the second law is a subtle thing. You want to know how many degrees of freedom you are considering in your definition of entropy. And when you do that, you say, okay, the entropy has effectively come down, but it never really violates the second law. And then that's how this can be consistent. Point one, what about point two? Point two is it true? Or am I just talking a lot of nonsense here? Well, I hope it's not nonsense, because theoretically, at least, it has some sense to it. But is it true of the world? Now, the important point here is, well, was there an eon prior to ours? If there was an eon prior to ours, is it possible that signals can have got through to us from them? Now, I said that photons can get through, but they probably aren't very strong and you can't see much. What else can get through? Well, I had to ask myself, what is the most violent thing I could think of which could perhaps send a signal from them to us? And then, well, let me give you an example in our current eon. I mentioned before that our galaxy has a black hole of about 4 million times the mass of the Sun. We are on a collision course with the Andromeda galaxy, which has a much bigger black hole, I think 20 times as big. We are going to collide. Okay, it'll be a few thousand million years. We will collide. When we collide, the black hole, well, they might miss, or they might just sense each other enough to capture each other and spiral into each other. If they miss the first time, the galaxies will go through and come back again and settle down, and yes, eventually these black holes will capture each other. When they do, there will be one incredible explosion in the form of energy being taken away in the form of gravitational waves. That's the gravitational analog of light, that is very weak under normal circumstances, but it could carry an enormous amount of energy away in a relatively tiny fraction of a second. Not a second, that's the wrong way to talk. Tiny fraction of time on the scale of everything I'm talking about. And the amount of energy will be sizable, a few percentage, probably, of the total mass energy of those two black holes. So you're looking at a really impressive amount of energy. Here's a picture now. This picture is meant to be a little, I've put in another dimension from the ones I just had a minute ago. This is the crossover surface. It's really a three-dimensional surface. This is the previous eon. This is our eon. This is our world line. That's us. We are looking back into the microwave background, which is created soon after this crossover surface. Now, in the previous eon, there will be now and again collisions between black holes. Bang, bang. These are gravitational waves. You have to look at the equations for this. The gravitational waves transform the energy into a little bit of a kick in the initial dark matter. And that's the material which is responsible for the deviations in temperature in the early cosmic microwave background. So you will see a slight effect, which to us, this intersection of this with this, will look like a circle. So you will see a circle in the cosmic microwave background over which the temperature is a little bit unusually uniform, and that's the way this works out. And the picture I had is something like a pond when it's been raining. You look at the cosmic microwave background, it should look like a lot of circles on top of each other. These would be these bang, bang, bangs going on all the time. And if you look at it at the right moment, just as crossover happens, you will see something. If you look at a pond, it looks like random, but you might imagine doing a delicate statistical analysis and picking out that there were evidences of these individual circles. So this is what I'm trying to say, maybe you can do. In fact, there's another feature of this, which is significant here, and that is, if you have a cluster of galaxies, there will be a few very big black holes, and they will look like where that cluster ends up. It will evaporate away eventually, but there will be a point in the cosmic microwave background sky, which is the center of this cluster of galaxies, and these rings should be centered on that point. So you would not only see rings of lower variation temperature, but there will be sets, concentric sets. Okay, so this, I tried to get people to look for this, and most people weren't interested, but my I had a colleague who is an Armenian, Vahe Gozadyan, and he did an analysis of this on the actual cosmic microwave background. I think I'll go over to the pictures on the computer here, if somebody will do that for me, that would be good. I want to show you the analysis he did first on the, yeah, that's the first one, good. The analysis he did the first on the, what's called the WMAP data, good, that's it. Looking forward to those two, yeah, let's show you two. This is the sky, sort of flattened out. This bit in the middle is where our galaxy is, and he said, well, all sorts of funny things may be happening. There's cut out a bit there, which is about 40 degrees width, 20 degrees up, 20 degrees down, and that's simply blotted out. You don't count. You look for rings, these rings being of, relatively speaking, low variance. The temperature is a little bit more uniform around the ring than elsewhere. And he looked for them which are concentric. So in this picture, in this WMAP map, which was a satellite called WMAP, W stands for Wilkinson. When he died, they put his name on as well. Before that, it was MAP, which was a nice acronym. It's hard to say WMAP now. But anyway, that was in honor of Wilkinson. And this was the analysis that Vahe Gozadyan did, looking at low variance circles. Now, there's a curious feature about this, is that there's a lot of clumping in the picture. I'll come back to that later. But he saw, depending on how much of the variance, I mean, what's your criterion of how low should be the variance be? And with the criterion he used here, he found, I think it's 253, 256, 252 centers of triple rings. And to see whether this is a genuine effect or not, there are lots of things you can do, and one of the things that he looked at was comparing with simulations. It's unbelievable how much argument there is about these things. So eventually we adopted a different method which doesn't use simulations at all. Can we, let's see, go to the next one. I need another thing to push button. Is that here? Oh, I used the computer. Okay, now that's it. I hope you can see it. I can't see it from where I stand very well. Let me tell you that the top picture on the right-hand side, or this picture, this is the picture we just saw. This picture is the picture of where the centers are. You may not be able to see them. I'll come to that in a moment in a different way. But what we did was to twist the sky, use the same analysis with more and more and more twists. And what that means is that you're not looking for circles anymore, but you're looking now for elliptical shapes. And this was the twist we applied, the sky twist, and this is the mathematics involved in that. And S equals naught means you're looking for circles. The next one means you're looking for slightly elliptical ones, almost circles. You can't tell that they're not circles from the eye. And then as you go down, they get more and more elliptical. This is roughly the shape. You see, that looks like a circle, that looks like a circle. A few percent away from the circle, and this is where it genuinely looks like an ellipse, twice as long as it is wide. And you see, you do exactly the same analysis, but now you're looking not for circles, but you're looking for elliptical shapes. On the left-hand side, oh, what's going on here? I'm not sure. I can't see the picture on the floor, I'm afraid. That's the left-hand side of this picture. Well, what you see, as you go down, the numbers go rapidly down. So even with a slight twist, which you don't even see much, it still looks like a circle to the eye, just about 1 or 2% difference. And the number drops by a factor of 3. And as you go down, the number drops and drops and drops and drops. So whatever you're looking at is very sensitive to them being circles. If they're even slightly elliptical, you don't see them. And on the right-hand side is twisting the other way. And you can see, again, they drop. Very many more you see when you're actually looking for circles. Okay. Now, that was the old... no, that was for 3. These were looking for circles where they're in concentric sets of at least 3. So the points, I don't know if you can see the points on the left-hand side picture here. The points are now marked out, and you can see where the points are, which are the centers of at least 3 circles. Now, if I go to the next one, which I hope I can do, this is a similar analysis, but now applied to the later Planck data. This is much more sensitive, with a much later satellite, and people often said, oh, well, you may see this effect in the W map. When you get Planck data, it's sure to go away. Well, it's even more obvious. You see these huge regions here. It's the same region we saw before. They're much more evidently there. And again, you do the... I'm sorry. This is not the Planck data. I apologize. This is the 4 circle. I'll come to the Planck ones in a minute. This is still W map, but we're looking for centers of at least 4 circles. And you see it's even more prominent. You see fewer of them. Before, you see about 56, I think. But the dying away is even more prominent than before. And you don't see anything at all. I don't know why you see a few here, but I mean, it's probably because this crowded region, things, you go from one circle and it latches onto another one, or something like that. But you can see that the effect certainly goes away very strongly. And with the 2-to-1 ellipses that we have in this picture here, they've gone. They've gone completely. So it really does depend on these features in circles. And the conventional explanation of the variations of temperature in the sky, well, I should explain a little bit about what the conventional explanation is. It depends upon inflation. You have to have this inflation, and during the early stages of inflation, there were some quantum effects, according to the theory, which produced fluctuations which somehow got magnified out in a way which doesn't quite make sense to me, but that's supposed to be what it does. Magnified up to a classical level, and then you see these variations, which should be random. There's no indication of why they should be in circular sets. I should also say that whereas the previous slide, let's go to the previous 2, yes, that one, almost exactly the same picture, was just recently obtained independently by some skeptical people, I should say. They did the same analysis that Dresden had done, and they found almost the same pictures as where the circles are and everything. So there's nothing wrong in the analysis of the circles here. People can argue about what it means. Is it random effects? Is it explainable by other processes? Maybe. But what's not in question is whether this picture is a real representation of something out there. It certainly is, independently confirmed. As I say, by skeptical people who think there must be some other explanation, but nevertheless, the features are there. Now, let me go on, back to where we were. This is the Planck data. These are now centers of at least 3 circles, and you do find these regions rather more prominent than they were before. You see some regions which were not prominent previously. This is a bit of a new one. One doesn't see it so much in the other data. This one is still there very prominently, and so are the others. So it's a feature which is also there in the newer, more precise, more detailed analysis. Observational data is still there. Now, this is an interesting picture. This is the centers of the... So you can't really see them very much. They're all on top of each other. But if you plot where the centers are, and that's what Roger did, these points are the centers in this previous picture. Now, there's a very remarkable thing I want to show you about this picture, which is obvious when you look at it. There are a lot of red ones here, a lot of blue ones there, and sort of intermediate greenish ones over here. Now, what does this mean? This is a color code. So previously he was looking at rings which had small variance. It's not anything about whether the temperature is warm or cool. The color here means red means warm and blue means cool. And why should the red ones all be clumped together and the blue ones? I was surprised when I saw this clumping and also with the colors. But when I see it, well, from the point of view of the Conformal Cyclic Cosmology, which I've been trying to promote here, there is an explanation. What it says, red means, it's very confusing this, because red means blue shifted. Blue means red shifted. I don't know why, this is not my fault. This is the color coding that people use. Red looks sort of warmer. And these are red-shifted and therefore cooler. There's another confusion. This is that according to the theory, the very distant ones, you think of those red shifts for galaxies, the really different ones will be the blue-shifted ones. And that is because, on this theory, the signal is coming towards us. Coming towards us means blue-shifted, and therefore, in this picture, red. Now, don't ask me to. It's confusing, but it's in a sense gone back to what you might expect. The blue-shifted ones, red in the picture, are the distant ones. This is extraordinarily distant, according to the theory, very, very big collection, supergalactic collection, huge galaxies with enormous black holes, and so many, many of these events. Another such a region, relatively closer, over here. Intermediate region, over here. And so that's the idea. Is that what we're seeing, or not? Well, the other point I would make is this remarkable clumping. It's not uniform over the sky. What does a uniform sky look like? So let's do a simulation according to the conventional type of picture. I'm not saying how many you should get, that's not part of the analysis here, but according to the conventional inflationary picture, it should be random over the sky, something like this. It shouldn't look anything like the picture we get here. Okay. That's where we were. I did something stupid probably, didn't I? No, I don't want anything like that. I don't want that either. That's another lecture. Okay, here is the random picture. Here is the actual picture. This random picture, I should say, also has color coding. You may not see it because the colors are pretty well uniform. That is also not explained by the conventional picture. So you have clumping, and the clumping goes along with temperature. That's consistent with this picture because, I say not predicted by it, because I thought maybe the previous eon was pretty uniform. Well, even our eon is not that uniform in many respects. And you're looking up at a particular phenomenon here with the collisions between supermassive black holes, and then there are certain regions where a lot of them are happening. Anyway, let me leave you with that. I should tell you that lots of people don't believe me when I say these pictures, so I should warn you that this is not conventional, but I think I need other people, if they have a different picture, to explain not just the non-uniformity here, but the fact that it's also circles particularly, and also that the color, that is to say the average temperature, seems to be correlated with the regions in which they come. Thank you very much.
Agradecemos. Sir, thank you very much. Ahora, como complete este tipo de acciones, vamos a solicitar al doctor Ernesto Lupercio Lara y el doctor Francisco Javier Turrubiat Saldívar, investigador de la Escuela Superior de Física y Matemáticas, para las preguntas y respuestas. Moderadores.
Muchas gracias. Bueno, dos pequeñas observaciones. Primero, quisiéramos agradecer a Roger por su extraordinaria conferencia y quisiéramos hacer un breve agradecimiento a las siguientes personas sin las cuales esto no hubiera podido ocurrir: Anabel Lagos, Estela Hernández, Jacob Mostovoy, Isidoro Hitler, Francisco Turrubiates, José Mustre y Ricardo Félix. Muchas gracias a ellos también por todo el apoyo. Y ahora las preguntas tienen que ser muy breves porque tenemos poco tiempo y mucha gente quiere hacer preguntas, muy al punto, y Paco va a elegir a la persona que hará la pregunta. Solo se puede hacer una pregunta, no dos, y yo voy a traducir la pregunta si la hacen en español. Entonces, procedemos.
I need to violate the rule, I'm sorry. But I'm going to make two questions. Very good.
That is not possible.
What the main question is this conformal transformation that is occurring at the end of each eon is to be thought as something physical taking place in the universe, or just reflecting our knowledge or the things that have meaning? I'm thinking in terms of, for instance, would the masses of the particles change? Would other massive quantities that one can assign to, for instance, a wave packet in the early universe, even if I have a photon, the wave packet will have a value of p squared that you could imagine as assigning it a mass. So how should I think about this?
Okay. Yes, let me try and answer your points. The first point is, yes, I regard this as a picture of the actual world, not how we look at it. It's what's happening. Now, of course, we're not used to mass fading out. And as I said, it was a conjecture in the scheme here, a hypothesis, which is that mass fades out. Now, I would say that there is one theoretical point, and I think related to your second part of what you were questioning here, namely that the way in which particles are classified in standard particle physics, the first thing you do is to classify them according to what's called the Poincaré group. So you say you have these notions of mass and spin, which are what are called Casimir operators. Now, I have to be slightly technical here, but these things are the things which commute with everything, and so they're meant to be absolutely conserved. So in a stable particle, the mass and the spin should not change. Now, this Poincaré group, when you have a cosmological constant, is an approximation. And you should really, a little bit more accurately, be talking about a thing called the de Sitter group. Now, the de Sitter group is the group you get instead of a Poincaré group when you have a cosmological constant. Now, this will only have relevance in extremely long timescales. In extremely long timescales, you ask that, okay, maybe the de Sitter group is a better way of classifying the particles. And if you look for the Casimir operators in the de Sitter group, they are not mass and spin anymore. So that mass and spin are more complicated. Well, spin, forget about it. I'm not saying that changes. It's the mass is the crucial thing. And that the mass is not a Casimir operator. And so there is a reason why it might not be absolutely constant. Now, that's not a strong argument, because I don't have a theory which tells us the rate at which the mass would fade away. And it would depend on the details of the kind of particle it was. I think if all masses faded at the same rate, it would be equivalent to a change in the gravitational constant. And I don't think it can be that kind. It's got to be where somehow you have many different notions of spin, many different notions of time, and these get out of kilter. And it becomes inappropriate to talk about a particular notion of time, because the masses change relatively, and over these long periods of time, you say, well, let's have a different description. And what you have to do is to produce a mathematical scheme where, okay, here you have physics as we know it, and then here we have crossover to the next eon. And then you put a little bandage across, a sticking plaster, where you have another kind of physics, which is described in a more conformal way, where you take into account how mass would behave as you go from one to the other, and you need equations for that. And I have equations which still have some questions about them. So maybe that's not I would say it's not finite. And it would have to employ something in which the mass fades out in accordance with you having to use the de Sitter group instead of the Poincaré group. But I think the questions are a bit technical here, and but I do regard it as real. It's just that it's not the kind of world we're familiar with, where mass is something which is a sort of stable thing, and you know what it means. And in this different context, it's even clear you need to have a different way of addressing the energy, because the notion of energy ceases to make sense as you cross over. There are other conserved quantities, and you have to convert your attention to these other conserved quantities. And it means doing a lot of physics all over again. But a lot of it has not been done. I think it's a big, interesting area, just theoretical. And we have a partial picture of what happens, and there are some puzzles still, and I hope maybe we or some other people will come up with definitive looking equations for that.
First of all, thank you for the lecture, Dr. Penrose. And I'd like to know, can or should I imagine black holes as doors from one eon to another? To say, in your model, can black holes be a way to pass on from one eon to the following?
Well, I know that the movie, what's it called, Interstellar, you have these wormholes, and I know Kip Thorne is very fond of those things. But you see, I have a lot of trouble, even in our eon, having wormholes, but much more trouble. And it's an interesting suggestion you make. But then you see, you would need a white hole to come out of on the other side. And these are anti-thermodynamic objects. So the black holes are very consistent with thermodynamics. The entropy goes shooting up when a black hole is formed. But if you had somehow a wormhole appearing in the next eon, nice idea, if that wormhole appeared in the next eon, it would have to be in what we call a white hole. Now, white hole violently violates the hypothesis that I have here of the low entropy in the gravitational field. Okay, I'm not saying it's an impossibility, but I'm saying it doesn't sit nicely with the motivational ideas that I was introducing here. So I would think less likely than the wormholes that we see in Interstellar.
Thank you.
Well, first of all, thank you for the lecture. I think my question is kind of related to that.
I'm sorry.
I think my question is kind of related to that.
Related to that, okay, yeah.
Let's say the rings in the cosmic drum background radiation, can a ring come from 2 eons back, or?
Signals. Well, are you talking about purely natural physical phenomena, or are you talking about advanced civilizations?
No. The rings.
Well, it's interesting. You see, yeah, you could get signals 2 eons back. In a certain sense, I claim we are seeing 2 eons back. Because you might say, why do you have these non-uniform distributions? Well, the uniformity of the distribution comes from very early in the previous eons, early stages, where the initial matter distribution, dark matter distribution, will be disturbed in one way or another. And why is it disturbed in one way or another? Because of signals coming from the eon before that. So the reason you see irregular distributions here, I claim, would be because of events occurring in 2 eons back. Now, it's more obscure, and I can't give you any picture of what 2 eons back, but these are early days. Maybe, eventually, people will be able to analyze these distributions well enough to say, look, there's evidence for something going on 2 eons back.
So, let's say, could you say there's a finite amount of eons? So, because if they were infinite, wouldn't it be filled with
Yes,
the rings?
of course, one could have different pictures here. I like to think it's infinite. Of course, it doesn't tell you without maybe 17 eons, and that's it. It seems to me unlikely. It would be much more probable, in my opinion, it's just what seems nice to me, is that the eons will continue indefinitely and it goes Alex zero in both directions.
Thank you.
One more question. I would like to ask why should you be so worried about the concept of entropy? Because after all, we are sometimes told that there exist various types of entropy. Many years ago, I was in the lecture of Bob Ward, in Yunnan, yeah.
Yes, sure.
And he was describing the evolution of universe, I think, in very critical situation, and was defining entropy. And from time to time, he was changing the definition of entropy because the entropy was in danger to diminish. So I think the entropy is secondary concept which was constructed on the basis of some dynamical laws. So if you propose some dynamical laws which are consistent, then why statisticians don't worry whether the entropy can be constructed or cannot be constructed? This is the question.
Perhaps I should clarify my position on it. First of all, let me say I have a lot of respect for Bob Wald, and he had a big influence on my thinking in these issues. So I have a debt to him in many respects. But I agree and disagree at the same time. You see, entropy, people often say, when I introduced my notion of the viral curvature hypothesis, they say, oh, well, Penrose is giving a definition of entropy which involves the viral curvature. And they say, this is his formula. No, I never say any formula. I think, in a sense, I'm agreeing with you that entropy is not a very good concept. It's a bit of which has to do with you have a phase space and you have a coarse graining and it's very arbitrary. However, it's not that arbitrary. And the point is that we're talking about effects, which entropy is a secondary thing. The primary thing is that the Big Bang was this very, very special kind. Forget about what the definition of entropy is. I've used that notion here several times, but just to give a general feeling, it's not a very good definition because, as I say, there are examples of many things where the entropy looks as though it's gone the wrong way. There are things called spin echo, all sorts of phenomena where it depends on which definition you're using, you might get a different answer. But this is such a huge effect that quibbles about exactly what your entropy definition is are nothing. The main thing is that you're looking at a specialness in the Big Bang which is overwhelming. And it does give us, forget about any definition of entropy, it gives us a kind of order that we see in the universe which is very time-oriented and which comes from the uniformity in the early universe. But I agree with you in the sense if you want to make entropy too precise a notion, you're going to run into troubles. And you're going to run into ambiguities, and you're going to run into things which look as though they violate the second law. But so there's a sort of, I have a little bit of an ambivalent point of view with regard to the question you raised. But I think that the questions are interesting, important, but secondary to what I'm saying here, because the effect is so huge that the quibbles about what entropy might mean are not going to make any difference.
Parece que habrá tres preguntas.
Born in year 20. I'm here.
Oh, you're looking at I just discovered.
So I have more than, it's not questions, I want to get your comment on this. So what I understand is you get two, if I may say, pillars for this theory. One is that in order to be able to expand and contract this at the end of and beginning and end of the islands, you need to have conformal geometry.
Sorry, yeah.
So to be able to glue them together, right? To make conformal transformations and this end of and beginning and end of the islands.
Yeah, but the point here, I mean, many people have suggested collapsing universes,
Right.
going way back to Coleman and
Right.
models that you have where universes. This is crucially different. I mean, there's a Steinhardt and Turok have a model where they have deep lanes colliding and so on. But all of those models have a collapse.
Right.
And the trouble with those is just this entropy issue, or if you like, or the black hole issue. If it happens too soon, as it does in their model, because they only have, what they say, a trillion years or something, there are lots of black holes around still. Those black holes come together and you get nothing like a smooth transition. This model is distinguished from those, as far as I know, in that there is no collapse. It's just that somehow the universe loses track of how big it is. Because the physics, mass fades away and the physics doesn't know how big it is. Okay, there are some subtleties and you have to look at how other features which keep track of things. And those things have to be in your equations. So you need equations to see how the evolution takes place. But those equations do not say that the universe collapses at any stage. It keeps on expanding, gets smoother and smoother, if you like, and that very smooth final stage is what gives you the smooth Big Bang in the next one. And you say, well, isn't it funny that the Big Bang is enormously hot and enormously dense, and the universe is enormously cold and enormously thinned out? Well, that's just a scale. You put the scale factor in, and cold goes to hot, and low density goes to hot density. So it's completely uniform. You just need a conformal scale applied to the remote future, and it looks very much like a Big Bang, and the other way around.
And that was my question. So, in order to have this, you need to have no massive particle at the beginning and end of each island to be able to do this.
Well, I would say it's asymptotic. I'm not saying there is a time when mass is gone. There is an asymptotic fade until it becomes such a small effect that then you need equations. So what is the fading out rate? And that is an issue which you have to make some hypothesis about. And I don't have a very good, I have a sort of hand-waving suggestion, which is a bit like a reflection in the Higgs field. So when the Higgs come in, when does Higgs go out, you see? So there's a sort of symmetry. That may be wrong, but it's the first thing I would probably suggest. But that's a ridiculously long time. That's far longer than the time that the black holes go away. It's absurdly long.
La penúltima pregunta. Sí, la penúltima, ¿verdad? Es la penúltima.
Sí, yo voy a hacer la pregunta en español. La tengo en inglés, pero por un giro. Son dos preguntas breves. La digo despacio. Doctor Penrose, en la nueva mente del emperador de los años de 1994-96, usted clasificó a las teorías físicas en tres grandes categorías: las soberbias, las useful y las tentativas.
¿Puedo traducir esa parte?
Sí.
Si no, se me va a olvidar todo. So, in the 90s, you classified physical theories in three kinds of hierarchies, from the ultra-precise extraordinary to the, what was the name?
Soberbias.
Superb. Superb was the best one. And there were a few, about 5 theories.
Yeah, something like that. Yeah.
And then no, I didn't say this theory. I hadn't called it this theory then. Superb is things like, well, not necessarily.
Like Euclidean geometry, I remember.
Euclidean geometry.
Euclidean geometry, that's right.
Superb. Yeah, it is superb. We use it all the time. We're building, we don't fall down. And these buildings, it works extraordinarily well. You know it's not quite right. Newtonian mechanics.
Newtonian mechanics, that's right.
Works extraordinarily well. Not quite right though. And then Maxwell equations, I forget what they were now.
Yeah.
Quantum mechanics works beautifully. I don't believe it. There has to be some level.
But do you believe in Euclidean geometry?
Superb. And then useful things like Kepler's ellipses, even the old epicycles.
That's right, Ptolemy's epicycles or something like that. That's right.
If you're
So what happens then?
La pregunta es,
another category that was, I didn't, misguided. Maybe it's misguided.
la pregunta es, ¿en qué categoría cae la cosmología conforme cíclica?
Oh, so now you have to judge your own theory. You have to tell me which kind is CCC.
When you see, I thought that was the question. I think maybe it's misguided. It's either misguided or pretty good.
Yeah. Pues es o está completamente mal o es de las mejores, ¿no? Una de las.
It's not totally a theory in the sense of equations which completely settle. So you see, Newtonian mechanics have very wonderful equations. And this is not, probably doesn't qualify, even if it's best, you see, for such a thing. Maybe at best it's useful.
En el mejor de los casos es útil. Es una de estas teorías fundamentales porque carece de ecuaciones completas para su descripción.
Yeah, here.
La última pregunta.
My question is about your picture. You wrote here, you put two pictures.
Yes.
The right hand side you put the conformal picture, and the other one is the normal picture of our universe. We know. In the right hand side, you need a conformal factor, but this conformal factor will translate into the other side, into the other picture, as a scalar field. Or more, this scalar field is in the right hand side. The conformal factor is multiplying the tensor, the energy momentum tensor, and you can translate in the other side to the other picture as if the scalar field is interacting with the matter, is thermal. Therefore, if we invoke the equivalence principle, this thermalicity will be related to an effective mass. Then you will have a effective mass scalar field in the left hand side. We should see these scalar fields. What is this?
Well, the thing is, with these, you can push these things from one place to another. And you see, one of the things that I think is in agreement with the kind of thing you're saying, I'm not quite sure. I mean, you can certainly treat the conformal factor as a scalar field. And this is a useful way when you say you have your dynamics down here, and then you go up to the crossover, and you want now to rephrase your dynamics in a way where the equations still make sense. And then you introduce a scalar field, as you say, which is the conformal factor. And the way you write Einstein equations is quite interesting, because that scalar field has an energy momentum tensor, and this energy momentum tensor contributes to the energy momentum tensor of the matter. However, it has the opposite sign. So what you say is that the energy momentum tensor of the matter equals the energy momentum tensor of the scalar field. And that is Einstein's equation, but formulated in a way which is useful when you're close to crossover. So, I mean, these ideas certainly play a role in what I'm saying, but you have to be careful about signs. This is one of the things. The scalar field attitude to the conformal factor is that it comes out with a negative energy momentum tensor. But then, when you cross over, there is an effective change of sign in the gravitational constant. There are these things which we need to look at carefully in technicality. And this change of sign compensates for the change of sign in the scalar field. And that scalar field now becomes a real field. So what you have in the Big Bang, the major contribution to the energy momentum comes from what used to be just the scale factor. And it's the conformal factor. And where does that come from? Well, I say, this is another feature which I haven't mentioned before in this model. You see, one of the big puzzles of current cosmology is not only we have this thing called dark energy, so what is dark energy? Well, I say it's just Einstein's 1917 cosmological concept. It doesn't say what its value is, but that's the way I would consider it to be in the equations. What is dark matter? The initial form of dark matter, I claim in this model, is that scalar field becoming a real field after crossover. So it now becomes the initial dark matter. It has to acquire a mass through a Higgs mechanism or something, and then the dynamics proceeds according to current cosmology. But then it has to decay away because it mustn't be there at the end. We've got too much of it. So the idea will have to decay ultimately. There are some little indications that dark matter does decay. I wouldn't put much faith in those at the moment. But there is a possibility that it will gradually decay away, not by the mass disappearing, but just as ordinary physical processes. As a kind of matter will decay away, maybe much quicker than the other processes we're talking about. Okay, the speculation is not that clear. But that's the picture. It's a bit like, I think it's in accordance with some of what you're saying.
Y les tengo una buena noticia. Este ion de preguntas terminó. Pero aparentemente hay un pequeño ion, no Big Bang, y tenemos dos más. Muy bien.
All right, they asked me for the question to be brief, but not for the answer to be brief. So it's a little bit along the lines that Daniel was asking originally. So my concern is, he asked about masses changing, but my question is concerned with scale parameters. So what I'm thinking is, when you're diluting, in particular, curvature, right? So when you get to the next eon, the curvature is way lower than they were in the beginning of the previous eon. So what I'm thinking is that you have somehow to change your measurements, your scale parameters, so that elementary masses are what change. I mean, I understood that Daniel asked about the reduction of masses, but I'm thinking about the masses of elementary particles and about curvature, because we're thinking that we begin with that curvature singularity, and we're fading away this curvature. So how is it that, so this new curvature would have to be a singularity from the perspective of the new physics of the new eon, if I'm understanding correctly. So somehow the physics of the next eon should be identical to, or should be translational from the physics that we have in this eon. So our scale parameters would have to change. The masses in the elementary particles and so on. So is that correct? Is that your vision, that somehow it thermalizes, and so what used to be small now is, what used to be big is now very small, and so on?
Well, I think in the scheme, I'm not sure if I'm answering your question exactly, but in the scheme, certainly, rest mass is not ultimately a constant. And it depends, I mean, particle physics is a very complicated subject. People talk about the standard model and all that, but you have enormous numbers of numbers in it. Do those numbers change? The way in which they're interrelated? It's a complicated question. But according to certainly observational limits that we have at the moment, there is no evidence that any of these numbers change. But you're looking here at timescales which are ridiculously long by comparison with any measurements that we've made. And so they could change. Now, there's also, I think, a little bit of evidence that they might well change, from what I was saying in answer to an earlier question. But they would not change uniformly. Now, I have colleagues in Oxford who have theories about how these masses come about, which I rather like. And these theories do tell us that the masses would evolve. They're sort of what are called running constants. And so over long periods of time, they would actually change. But not uniform, depending on which particle you're talking about. And there are different contributions to the mass, not just the Higgs contribution, but you have conformal anomalies and various things which are very complicated. Now, particle physics is a subject which is much too complicated for me. It's, compared with general relativity and cosmology, is far more complicated. But people have a good theory which works pretty well now. To what extent that will survive, I have suspicion that there will be gradual changes in these numbers. None have been observed so far. Things like fine structure constant is observed very precisely not to change. But maybe this, from the eon's point of view, will be trivial at the time.
Y ahora sí es la última pregunta.
So this picture you have here, is it like direct evidence of the eons before, or is that still in question, and could that be explained by some other reason?
Well, I mean, if there's another reason, I hope someone will tell me. The reason I say, I mean, it's pushing the problem back in relation to this previous question. The problem is pushed back to the eon before that, and then to the eon before that, no doubt. So I say there are irregularities which will propagate from eon to eon in a way which I hope is stable. I mean, they're interesting questions, but maybe the perturbations get worse and worse and worse. It's terrible after a while. Or they might settle down. In relation to an earlier question, I was saying, well, my prejudice is to believe that they settle down, and it's pretty well the same all the way. But what you see here, according to this picture, is that these points represent black hole, multiple black hole collisions in an eon prior to that. Very distant, in fact, so distant that in the current cosmology pictures, they are outside what we call our particle horizon. There is a distance we can look out to, and this is beyond that. People say you can't look beyond that, but that's because they don't have other eons. In our eon, you can't look beyond that. But in the previous eon, you can see, according to me, the collisions between black holes in some region which is very dense. Well, not dense, very populated by huge numbers of enormously massive black holes. And why is that there? Because of something in the eon before that. Well, who knows? But I am saying that there is a sort of explanation. I'm not saying why it's here, I'm not saying why this one's there, or that one's there, or why that one is there. And there's probably some others hiding behind here. I should say also there's a published group, and they see patterns very similar to this. They have a bigger exclusion region, but they certainly see that one. And I think they see a bit of this one. This one is not seen so well because the exclusion region cuts all this out. But it's consistent with this picture. But I'm not saying why these things are so non-uniformly distributed. I'm just saying that it is consistent with this picture. And that the fluctuations in temperature are not caused by some random quantum effects, which would give you a uniform distribution, very uniform, like the simulation I showed you, not like this. So it seems to me it's a partial confirmation of what CCC says. It certainly is not a very strong one because it doesn't tell you why the previous eon was like that. But it does seem to be rather in contradiction, as I see it, with the current picture. Because the current picture would say, whatever is the source of these particular features, that source ought to be pretty uniform over the sky. And that's not what we see.
Pues muchas gracias por sus preguntas. Agradecemos la participación del profesor. Y mañana, en la segunda conferencia de Lefschetz, que será de contenido ligeramente más matemático, hablará de testores. Y en el CINVESTAV recibirá el doctorado honoris causa por parte del Centro de Investigación y Estudios Avanzados del Instituto Politécnico Nacional. Y ahora, algo más.
Sí, gracias. Y es que continuamos con como se estila en este tipo de eventos. Agradecemos a nuestro conferencista, Sir Roger. Thank you very much. Y ahora invitamos al muy digno representante de nuestro señor director, doctor Julio Gregorio Mendoza Álvarez, secretario general del Instituto Politécnico Nacional, para hacer entrega de dichos reconocimientos.
Muchas gracias. Muy buenas tardes. Pues después de oír esta magnífica conferencia de Sir Roger Penrose, de oír también estas ideas tan sugestivas acerca del Big Bang, de ciclos de expansión, compresión, de la idea de la segunda ley de la termodinámica, que por allá Bogdan decía que había que repensarla mejor, pero la idea como tal de que la entropía nos da siempre el sentido del tiempo y que en algún momento dado esta colisión de agujeros negros pudiera resetear en un momento dado el ciclo, la dirección del tiempo, ¿no? Creo que son ideas fascinantes. Voy a dar lectura al reconocimiento que da las conferencias Solomon Lefschetz al profesor Sir Roger Penrose. Y tiene esta denominación. Roger Penrose Lefschetz is the 2015 Lefschetz Lecturer for his profound and imaginative contributions to our understanding of the mathematics and physics of space-time, as well as for his relentless advocacy for the public understanding of science. Y esto es firmado por Jacob Mostoyo, jefe del Departamento de Matemáticas del CINVESTAV. Thank you very much for your incredible conference. Y también, de parte del Instituto Politécnico Nacional, le queremos dar unos recuerdos al profesor Penrose. Hablaba de relojes y, bueno, pues hablando de relojes, el calendario azteca creo que puede ser muy significativo. También en la Universidad de Oxford, de donde es profesor Sir Roger Penrose, pues los colleges llevan un distintivo mucho en las corbatas de cada college, entonces le queremos también hacer entrega del distintivo de la corbata del Instituto Politécnico Nacional. Y en el año 2005, que fue el año maravilloso de los papers de Einstein, se hizo un evento aquí en el Politécnico, en la Escuela Superior de Física y Matemáticas, se hicieron estas figuras de Einstein con la sudadera del Politécnico, entonces también se la queremos entregar al profesor.
Bien, de esta forma concluimos este magnífico evento. Agradecemos infinitamente todo lo que va. We appreciate your participation here in the Polytech. It was an honor for us. Y para todos ustedes que tengan una espléndida tarde. Gracias.